All right, so welcome to Friday. Happy Friday, everybody. We are going to continue our discussion on these higher order differential equations, and specifically today we're going to look at variation of parameters, how we're going to adjust what we did before to this new kind of situation. But before we go there, homework questions. Anything out there that we want to see?
Number 15 on 8.5.
All right, let me just write this down. 8.5, number 15. All right, any others? Can add to the list. All right. Well, then let me go ahead and share my screen and we'll go find that and take a look at it. So hopefully soon you'll see my screen. All right. I'm actually really close here. Okay, so for this one, number 15, it says, what does it say? We just want to use the Laplace transform to solve the initial value problem. And then, yeah, there you go. So let's come back down to 15. So we've got y double prime plus 2y prime plus y. And that equals e to the t when we're between 0 and 1. And then it's equal to e to the t minus 1 once we get to 1 and beyond. And then we've got initial conditions. Y of 0 is 3. And y prime of 0 is equal to negative 1. All right, so I got everything on there. Let's go to the whiteboard. All right, so we're going to use Laplace transforms, but what should we do first? Before we take a Laplace transform?
Separate the right side into its individual bits.
Okay, so, and I don't know if what you mean there, Thea, is to sort of do it as two separate things. My suggestion is let's use the unit step function just so that we can write it all out as one thing, and then we know how to find Laplace transforms of those. So as a, we'll call that guy f of t, using step functions, well, we're starting with e to the t. So it's just good old e to the t. But then we're going to use the unit step function at 1. So once we hit 1, we need to turn something on. And really what we have to turn on is just negative 1. This is one that I wouldn't actually go through all the steps to get. I just go, it's just minus 1, because that's all we're doing is taking away 1. But you can think of it as this, we're turning on e to the t minus 1, and we're turning off e to the t. So hopefully you remember that was a suggestion I made. Think of it as what we're turning on and what we're turning off, and then do the subtraction. But you can see how that becomes just minus 1. So the forcing function is just e to the t minus the unit step function of 1. All right, so we all good with that? All right, so now let's go ahead and take Laplace transform. So we'll do Laplace transforms of each side. All right, so if we start with the second derivative, the Laplace transform of the second derivative is going to give us s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. So we developed that quite some time ago, but that's the Laplace transform for the derivative. Okay, or sorry, for the second derivative. So then we need to add 2 times the Laplace transform of y. So that's going to be plus 2 times, sorry, the Laplace transform of y prime. So that's going to be s times the Laplace transform of y minus y of 0. All right, and then we add on the Laplace transform of y. So that's what we're going to get from the left-hand side when we take the Laplace transform. All right, so far so good. All right, so now let's take a Laplace transform of f of t. So e to the t, we know its Laplace transform, which is going to be 1 over s minus 1. E to the at, its Laplace transform is 1 over s minus a. So this one, it's a is 1. All right, and then we're going to subtract the Laplace transform for u sub 1. And so the unit step function, it's always e to the minus cs. So this will be e to the minus s, because c is equal to 1. And then we divide by s. All right, so there's our Laplace transform. So now it's a matter of solving for L of y. So let's put in our initial conditions, right? We had y of 0 was equal to 3. So we'll change those things to 3's. Now we've got y prime of 0 is equal to negative 1. So we'll change that to a negative 1. Okay, so let's rewrite this. And I'm going to also group all of the Laplace transform pieces together. So I'm going to get an s squared plus 2s plus 1. All of that times the Laplace transform of y. And then the remaining pieces, I'm going to get minus 3s. I'm going to get a minus 1, so that's plus 1. And then a minus 6, so I think that's a minus 5. And so then here was the derivative, or sorry, not the derivative, Laplace transform of the function itself. So we good so far? Please, please, please double check my algebra. All right, so now let's solve it for the Laplace transform of y. So we've got this. I'm going to write it as s plus 1 squared, just because we're going to want that eventually anyway. The Laplace transform of y is equal to s minus 1 times e to the minus s divided by s times s minus 1 plus 3s plus 5. Actually, I don't know why I just combined those. I don't know if that's actually going to help us. But, But then let's divide by the s plus 1 squared. So we end up with, I'm going to break it back apart. The Laplace transform of y is equal to 1 over s minus 1 times s plus 1 squared minus e to the minus s over s times s plus 1 squared plus 3s plus 5 over s plus 1 squared. And now comes the fun with partial fraction decomposition. All right, so who was it last time? Was it you, Thea, who asked about using something to do the partial fractions? So I can't hear you. I think you're on mute.
Oh, yeah, I was the one.
Okay. So totally, like,
Yeah.
when you get to this point, please feel free to throw this into your favorite program, you know, whether it's Symbol Lab or whatever else. So I don't know, you want to do that for me? Maybe that's what you're doing.
Yeah,
right now.
I'm doing it right now.
Okay, cool.
Okay, so the first chunk, the 1 over s minus 1, s plus 1 squared, right? That's 1 over 4 times quantity s minus 1 minus the same, s plus 1. 1 over 4 times quantity s plus 1 minus 1 over 2 times s plus 1 squared.
Okay, does that look right?
Yep.
All right. So that's the breakdown for the first fraction.
Let me do the next.
I'll tell you what, actually do the last one next.
Last one? Got it.
Yeah.
This one is 3 over s plus 1 plus 2 over s plus 1 squared.
Okay. All right, so now you can do the last one. And for that one, just do 1 over.
Yeah.
Because the e to the minus s will be a multiplier on it.
And the next one is 1 over s. I mean, minus 1 over s. Plus 1 over s plus 1.
So when you gave me that minus and that plus, did you already distribute the minus sign through?
Yeah, I already distributed it, so.
Okay.
Plus 1 over s plus 1. And then 1 over s plus 1 squared.
Is the sign on the 1 over s plus 1 squared the same?
Both of those are, the 1 over s plus 1 and the squared, those are both positive. But the 1 over s is negative.
So we're still going to be subtracting that.
You could switch the one on the outside to positive because I already threw the negative.
Okay,
yeah.
I got you. Whew. All right. So here we are. So now we get to go backwards.
Yep.
Right, now we need to go in reverse and figure out what are all these different things. What do they equal? If we inverse Laplace. Okay,
Also,
so I'm
that
going to
Laplace
consult.
table that you posted was the
Yeah.
same one that I posted on
Oh,
the
really?
screen. Yeah, I took a look at it. I was like, oh, it's the
I'm
same
not
one.
surprised. It was one of the first ones that popped up on Google,
Yeah,
and I think it was like Stanford or something. And I'm like, well,
yeah.
can't trust Stanford for a Laplace table. Then I don't think you can trust anybody.
Yep.
Okay, so let's start breaking these down. So all of these that are just an S plus or minus a number, those things are exponential. So what we're going to get then is that y is equal to 1/4 e to the t. So that 1/4 is a constant multiple, but the s minus 1 tells us we get e to the 1t. And then we're going to get minus 1/4 e to the minus t. That was this piece. Okay, so now the 1 over s plus 1 squared, that's actually going to give us a t times e. So that's actually going to be a t e to the minus t. So we're going to get minus 1/2 t e to the minus t. You know that it's e to the minus t because of the plus 1. And then you know that there's a t out front because of the fact that it was squared. Had it been cubed, it would have been a t squared e to the minus t, and so on. Okay, so that's 1, 2, 3. So the next one's 3 over s plus 1. Well, that's another 3 e to the minus t. The 2 over s plus 1 squared, well, that's going to be a plus 2 t e to the minus t. So there were those 5. And if you noticed, there are some of those that we can combine. Right? Some of them are exactly the same form. So we will put those together in a minute, but I just wanted you to see the 5 as they came. Okay, but now we've got that e to the minus s. Okay, well, the e to the minus s, that tells us that there's going to be a u1. So there's going to be something that turns on at 1, which makes sense because of our original differential equation. So then the question is, what is it that turns on? Let me actually write this on the next line because I think I can get it all in one here. Okay, so what we need to do is figure out what are all these different things going to be. All right, well, minus 1 over s. 1 over s is just 1. So we're going to get negative 1. Because it's a constant, we can just leave it as it is. Everything else we're going to have to shift, right? But that one is just minus 1. Okay, the 1 over s plus 1, that's e to the minus t. But instead of just having a t, what do I have to put?
Is it plus 1 or
It's not plus 1,
no?
it's minus 1.
Minus. Oh, because okay.
Because we're shifting it. Think of it as we're taking that original function, whatever this was, and we're shifting it over to start at 1. So that's a right-hand shift, which means that needs to be a minus. Okay, so that was that piece. And then the 1 over s plus 1 squared. Again, we knew that was going to give us a t times e to the minus t. So instead of t, it'll be t minus 1 times e to the minus t minus 1. So in the brackets are the 3 pieces that were down here in the parentheses, but each one of them got shifted t minus 1. We just don't see it in the horizontal shift in this guy because it's a constant function and you shift it horizontally, it doesn't change. And then the u1, that came from the e to the minus s. So had it been like e to the minus 2s, this would have been u sub 2, and all these would have been t minus 2. All right, so I think I actually will just leave it here. But like I said at the beginning, realize that we could combine these and get like a, what is that, 11 force e to the minus t and a plus 3 halves t e to the minus t. But anyway, so is that better, Thea? Again, you're on mute. Thea, you're on mute. I can't hear you.
Damn it.
No worries.
Yeah, I just found it a bit tricky. I'm just getting used to it, so.
Yep. And there's a lot of algebra, but obviously feel free to use your technology when it comes to the partial fraction. All right. So cool. All right. Well, again, Laplace transforms, take it for what they are. They're a way of doing all of this without doing any calculus. The calculus is all done in creating the chart. And once you've got a chart of Laplace transforms, then it's all algebra. And especially back in the day when we did not have technology, the algebra was doable, the calculus cumbersome. All right, cool. Well, let's finish up our discussion of these higher order partial derivatives today. And remember, all we were looking at were things that look like p naught of the nth derivative of y plus p1 times the n minus first derivative plus all the way down here to pn times y. And we'll go ahead and write here f of t. But there's your generic higher order. And what we've seen up to this point is that if you want to find the homogeneous solutions, you do exactly the same thing as we did before. If they're constant coefficients, you just make your polynomial. It's just a bigger polynomial. So we have to find more roots. But the process is the same. The more roots makes it more likely that you have repeated roots. So we definitely have to remember to keep multiplying by t's as many times as the multiplicity suggests. But anyway, so we saw that was the same. And we talked also last time about how undetermined coefficients works exactly the same way. And what we really saw is that the only difference is that it ends up being a larger system of equations. There are more unknowns that we have to find, but in terms of process, it's identical. Okay, so, but what we want to talk about today, or what I want to talk about today, okay, it's not what I want to talk about, what we're gonna talk about. Right, if I had my way, we'd be talking about high quality root beers and the baseball game that happened last night, and yeah, except, yeah. Anyway, but let's go ahead and talk about how we deal with variation of parameters. Okay, because I want to look at this one. The big reason is that we saw that this method variation of parameters actually was a little bit more robust. It allowed us to take care of differential equations where that f of t was uglier. Wasn't necessarily a nice form. Like I think the very first one we did was something where it was like equal to secant or some sort of nonsense. But we need to talk about this. Is there a way to extend variation of parameters to higher order? Okay, well, obviously there is, otherwise I wouldn't bring it up. But I want you to think about what we did when we set up variation of parameters before. Like, what was the process for this one? So go back to a second order. So we've got a y double prime plus y equals natural log of t or something like that. How did variation of parameters work? What did we do? Or how about we start here? What do you need to do variation of parameters? All right, in order to do variation parameters, we needed to have the fundamental set. We need a fundamental set of solutions for this. Okay, so this is still going to be the same. We have to have all n in a fundamental set. So I'm going to write here, we need a complete fundamental set. Well, already you can see that this is going to be a little bit more complicated. Because before, with the second order, it just meant we needed to have two. And sometimes you could find a second one if you knew one of them. And so maybe finding one's not terrible. But now we're going to need n of them. So it could be a challenge to try to find all of them. But this is what we're going to need, just like before. Okay, so then the next thing that we did when we did variation of parameters, when we built our method, we said, okay, well, let's look for a particular solution that's some linear combination of those fundamental sets, right? So we basically said we're looking for a YP that takes on the form U1, Y1 plus U2, Y2 plus, now we're going to have to extend this all the way to UN, YN. And the reason that we could do this is we know that every solution is going to have to be formed from this fundamental set, because the fundamental set is a basis, right, using linear algebra terminology. All right, so then what we did is we put this into the differential equation and we put on a couple of conditions. There was that really weird one that at the time you probably felt like, why was I doing this? It was where y1 times u1 prime, excuse me, plus y2 times u2 prime equals 0. I basically had a free choice, right? Well, we're going to do exactly the same thing here, except now we have more free choices. We actually have n minus one of them. So here's what we're going to do. We're going to attach these conditions. We're going to make it so that y1 u1 prime plus y2 u2 prime plus down here to yn un prime equals 0. That's pretty much exactly the same one that we did before, just now with n of them instead of just the 2. But we're also going to put on that the same thing happens when we look at the derivatives of y. So if we take y1 prime times u1 prime plus y2 prime u2 prime plus all the way down here to yn prime un prime, we'll make that equal to 0. And we'll continue this until we get to the n minus first derivative of y. So each one of these is totally fine because, again, of the fact that we have n different functions, we can have n minus 1 conditions that we put on them. Oh, I lied. This last one, this is actually equal to our function f. So the last one we don't want to set equal to 0, but the one, all the ones before it we do. But this last one we want to set it equal to f. And this is similar to what we did last time. The first condition, even though it had only two, it was y1 u1 prime plus y2 u2 prime equals 0. And then the other one was y1 prime u1 prime plus y2 prime u2 prime equals x f of t. And so we're going to do that again. All right, so what this does is the same thing it did last time, which is create a matrix equation. Right? This is a system of equation. The unknowns are the ui primes. They are part of every equation. And so if we turn that into a matrix equation, what we see in our matrix is y1, y2, all the way down here to yn. The next row is y1 prime, y2 prime, all the way to yn prime. And then we can carry this down to the n minus first derivative of each of these things. And that is now times u1 prime, u2 prime, down to un prime. And what that's going to equal is a whole bunch load of zeros and then f of t. So hopefully you're seeing that we're just expanding what we did when we were in the the second order case. Then we ended up having a 2 by 2 matrix. Now we're going to have an n by n. So this will get uglier, obviously, as we get higher order. But what's beautiful is that it's got the exact same process. And if we think of this as a matrix equation, let's call it, say, ax equals b, we know that x then is a inverse times b. And so we're going to do exactly the same thing. We're going to find this a inverse and then multiply it to b. Now, when it was the 2 by 2 case, it was super fast, right? It was really easy to get it. But we're going to use the same process. All right, but I know what you're thinking. Well, what you're probably thinking is, thank God for Symbolab, right? Because we can put this matrix in and then Symbolab will do the calculation for us. But even if you're not thinking that, you're thinking, Jesus, finding the inverse of a matrix of any kind of size is really kind of a pain. Well, it turns out you don't need to know the whole inverse. The whole inverse doesn't matter. And that's because of all of these zeros. So I want you to think about the matrix A inverse, right? It's got whatever's in it. But think about multiplying that to this thing that's all these zeros and f of t. So you take the first row of A inverse and you multiply by b. The only element that matters is the last one. Everything else is just going to go away. Okay, go to the second row. Second row times this thing, same deal. Only the last one matters. Same with the third row, fourth row, fifth row, and so on. So in reality, we don't need A inverse. All we really need is its last column. Because the last column is the only thing that's going to remain once we do this multiplication. Okay, so this is such a big thing that I'm going to even write it. Right, we don't need all of A inverse. Only the last column. Now, if we're using Symbolab or some other technology to find the inverse, not a big deal. We're just going to take the whole inverse anyway. But you can imagine if you're having to do this on your own, right? So we're on that deserted island, and the only way off is to solve a differential equation using variation of parameters. We can save ourselves a little bit of time by just looking for that last column. So again, like you think about the last column, you can actually find the column of an inverse by using the the cofactors. So don't know if you remember cofactors and minors and all that sort of thing. But basically, that's what we can do here. We can just figure out what the minors are with that last column in order to figure out what we need to integrate to get our u's. Okay, so let me show you. Let me show you with an example of how we're going to do this. All right, because we're just going to take that last column times b, which means the entries in each of those columns, or in each entry in that column times f, and then those get integrated to find our u's. All right, so let me give you an example. I think it's a lot clearer when we actually do it. And we won't get too crazy. Let's just go with a third order differential equation. Well, let's go with y triple prime minus y double prime minus y prime plus y. And let's make that equal t. Okay, so this is one that we wouldn't use variation of parameters on, right? Because of the fact that it's equal t, you would just probably go with an undetermined coefficient and see what you get. But let's practice variation of parameters with this. So first things first, we got to get a fundamental set. So let's make the polynomial. It's going to be r cubed minus r squared minus r plus 1. We can factor by grouping. And you got r squared minus 1 times r minus 1. So this is equal to r plus 1 times r minus 1 squared. So in terms of our fundamental set, we've got y1 equals e to the minus t. y2 equals e to the t, and y3 equals t, e to the t. All right, so very first step, we got to get our fundamental set. So if this was the homogeneous, we'd be done. Obviously it's not, so we have to go another step. All right, so let's go ahead and create a Wronskian matrix. And it totally doesn't matter what order you put these in. I don't know if you remember that when we said y1 and y2. It extends. You can do them in any order you want, right? So just for the hell of it, how about we go e to the t, t e to the t, e to the minus t. All right, well, then let's see what our matrix is going to look like. So we need the derivatives. Well, that'll be e to the t and e to the t here, minus e to the minus t and plus e to the minus t in that third column. And then for the next one, or for the t e to the t, this one we have to use the product rule, but I'm going to help us out a bit. The derivatives are t plus 1 e to the t and t plus 2 e to the t. All right, so there's our Wronskian matrix, or the matrix that I called A. So now we need to get its inverse. Okay, well, I'm not going to get its inverse. I'm just going to work on that last column. But hopefully you remember that when you find an inverse, you always have to divide by the determinant of this matrix. So we need to get its determinant anyway. So let's get that. So if we call this guy A, the determinant of A, I'll let you check this on your own if you want. But what we end up finding is that this is equal to 4e to the t. All right, so there's its determinant. So now, here's what we need to do. If we want to find the different entries in that column, we can basically make use of the like sub determinants. But let me show you how we can make this a little bit easier. Because right now with all those e to the t's, it's kind of ugly. But notice every single one of those, we can factor out an e to the t, right? So like we could factor out e to the t's, we could factor out e to the minus t's. We can do that to help us out a little bit when it comes time to calculate these things. So let's look at finding, say, the ijth entry of an inverse. All right, so does anybody remember how to find that? Like the quick way instead of going through the whole thing and finding the entire inverse? It's something that you should have seen in linear algebra. And maybe not. I mean, I'm not really sure. So what we do is we actually look for the ji minor. I don't know what kind of notation you guys used, but so I think of the minor, the determinant of the minor. And then, so you swap the j and the I, so you look at the determinant of that minor. And then you have to divide by the determinant of A. So like this is how this would go. So let's start with, I want the 1, 3 entry. So to get the 1, 3 entry, I'm going to look at the 3, 1 minor. So the 3, 1 minor, 3, 1 is this spot. So I cover up that row and that column, and I look at what remains, and I find its determinant. Okay, so let's think about what that determinant looks like. We're going to get a minus t, because the e's cancel, and then minus t plus 1, because again, the e's cancel. And so we would get minus 2 minus 1. So in terms of A inverse, it's going to look like, I don't know, we got some stars here. I don't care about the first two columns. But this next column, this is going to be minus 2 minus 1 over 4 e to the t. Oh, sorry, not minus 2, minus 2t. Minus 1. Okay, so that's in the 1, 3 spot. So the next one I want is the 2, 3 spot, which means I need to come to 3, 2, which is this one. So notice that all I'm doing is I'm going across the bottom row. But now I ignore that row and column, and I figure out what is the determinant of this minor. Okay, so we would get minus 1, minus 1, so that'd be minus 2. And then we'd have to divide by the 4 e to the t. But instead of minus 2, we actually get a plus 2 in that spot. And this is the whole, you go plus, minus, plus, minus, plus, minus, plus as you move along from spot to spot. basically add the row and column numbers. If it's even, you get a positive. If it's odd, you get a negative. I might be speaking Greek for you guys, but hopefully there's maybe a little bit of stuff that's kind of popping back. Okay, so then when I finally want to go to the 3-3 spot, I need to do the same thing for the 3-3 minor. Okay, so this time the e to the t's don't go away, because e to the t times e to the t is actually e to the 2t. But we're going to get t plus 1 of them minus t of them. So that just leaves us 1 e to the 2t. Get e to the 2t over 4 e to the t. All right, so there's the part of A inverse I care about. I don't care about the rest. I only care about this. All right, so now what's the point? Well, let's go back and remember what we're doing with this, right? We're taking A inverse times B. So we're going to take this and we're going to multiply it by 0, 0. What did I say we had? E to, no, T? E to T? T? I think it was T.
It was T.
So T. So when we do this multiplication, what we find is that U1 prime is equal to minus 2t squared minus t over 4 e to the t. That's just these two multiplied together. U2 prime, that's going to be, well, the 2 and the 4 are going to reduce there, so let's just make this t over 2 e to the t. And then U3 prime, the e to the t goes into e to the 2t, right? Divides into that, makes it just e to the t. So we get t e to the t over 4. So I'm going to stop here with this problem because you know what to do now, right? Here it's really easy. Now we're going to integrate. That's going to give us our U1, U2, U3. And we're going to multiply those against their corresponding y's, right? And so I think the way I created my matrix was numbered differently. I think we had y1 was e to the t, y2 was t e to the t, I think. Y3 was the e to the minus t. But as long as you keep the same order, right, it doesn't matter how we put them in the matrix. We just have to remember that the corresponding numbers that come out here, or the corresponding functions, those have to multiply to the functions that we put in those respective columns. All right, so that then would give us our solution. So the process here is identical. It's just longer because it's harder, right? I mean, it's bigger matrix. It's going to require us to do more because of those minors, but this is the general idea. So let's do a fourth power or a fourth order. All right, I want to go ahead and show you a fourth order so you can see how we'd go about it. But it's really the same idea. And the key is to remember that all you need to do is build the last column of A inverse. So you really only have to look at the last row of A, go along the last row of A and find those minors. And it'll speed up the process a lot. And you'll see that for sure in this case where we do a fourth order. But before I move on, we okay with the process-ish? Okay, well, let's just do one more here, get a fourth order set up so you can see how that goes. All right, so how about this? Let's say we've got the fourth derivative plus 2 times the second derivative plus the original function, and let's just say that it's equal to sine. So again, this is not one that you would use variation of parameters. Since you've got sine, you would probably go ahead and just do undetermined coefficients. But let's go through this process so you can see how it goes. All right, so first things first, we got to find the fundamental set. So we've got r to the fourth plus 2r squared plus 1 equals 0. So that's r squared plus 1 squared equals 0. So we're going to get roots of plus or minus I and plus or minus I again. So that tells me my fundamental set are going to be cosine, t cosine, or how about sine, cosine, sine. We usually put those together. And then y3 is going to be t cosine, and y4 is going to be t sine. So let's build our Wronskian matrix. So I'll go ahead and put them in the order that I wrote them. So we have cosine, sine, t cosine, t sine. All right, so now we just got to take derivatives. So we got going down the first column, minus sine, minus cosine, sine. The second column after sine comes cosine, minus sine, minus cosine. And then comes the fun part. He says sarcastically, because now these are going to require product rule, right? But like this next one will be cosine minus t sine. And then we're going to get minus 2 sine minus t cosine. And then that's going to give us minus 3 cosine plus t sine. Pretty sure that's what those derivatives are. And then t sine, we get something similar. We get sine plus t cosine, which then gives us 2 cosine minus t sine. And then lastly, minus 3 sine minus t cosine. And I apologize, I ran out of space. So I'm pretty sure about those derivatives. Please, though, double check. But I think they're good. All right. So now the fun begins. Because think about what we need to do if we're going to do this a long way. First, we need the determinant of this matrix. We need to actually calculate the Wronskian. What? All right, we don't want any part of that. But I want to remind you of some tricks that you can pull to help you find that. You remember your row ops? You remember them, right? There's the row swap, then multiply a row by a constant, and then multiply a row by a constant, add something else. You can actually use that to help you a lot in terms of finding this determinant. For example, take the first row plus the third row and store it in the third row. I'm going to really kind of abbreviate things here. So I'm just going to write cosine and sine, but obviously there's a t in there. And the second row, I'm going to leave it as it is as well. Okay, but check this out. If we take the first row and we add it to the third, notice we get a 0, a 0, a -2 sine, and then a 2 cosine. Now I'm going to do the same thing, second row plus fourth row, and store it. So that's going to give me a 0, 0, and a -2 cosine, and a -2 sine. And what I know is that these two matrices have the same determinant. That row up, the multiply a row by a constant and add it to something else, that doesn't actually change the determinant. So this is a lot faster now if I want to find a determinant, because hopefully Larry showed you, you can find a determinant by expanding along a row or a column. And so in this case, like I would expand about the first row, for example, or sorry, first column. So if I have cosine, it's going to be cosine times the determinant of this thing. Well, the determinant of that's going to be cosine times the determinant of this 2 by 2. The determinant of this 2 by 2 is 4 sine squared plus 4 cosine squared, which is 4. So in terms of the determinant of A, what I've got right now is 4 cosine squared from this one. Then I can go to sine and do the same thing. Now I have to make it a negative because I'm in the next spot because it goes plus minus plus minus. So a negative negative sign is sine. Now if I look at this next column, the only one that's non-zero is that sine. So I've got sine times sine is sine squared times that same derivative. So that's plus 4 sine squared, which actually equals 4. So it turns out that the determinant of this 4 by 4 matrix, this horrible looking thing, is just 4. Put it in a symbol lab, it should tell you it's 4. Put it in your TID9, it'll tell you it's 4. But these are just little tricks that I've picked up over the years because, well, I don't usually have technology available. Plus, you know me and my trig. Okay, well, so that's the Wronskian. So now, if we're going to create that last column of A inverse here, we're going to go along the last row, cover up rows and columns, and find the determinants of those 3 by 3 matrices. Okay, so for example, if we're going to go for the top entry in that last column, we're going to come over here to the first entry in the row, and we're going to cross off that row and that column. And you see that leaves me a 3 by 3 matrix. So I need to find the determinant of that 3 by 3 matrix. Well, here's the good news. 3 by 3 matrices, we know how to find those determinants. I call it playing asteroids. You remember that? So you can kind of go down the diagonals. If you go down diagonally to the right, whenever you hit the edge, you come back to the other side. Right? So you calculate those 3 going to the right are positive, the 3 going to the left are negative. You can add those up. You can find its determinant. So it can go kind of quickly. I think I'm not going to do that here because I think none of you actually really care. You're just going to go ahead and plug it into your technology and find those determinants. But this process actually is not terrible, especially with technology. And what it's going to allow us to do is actually find solutions to these things when they're not nice forms. And like I said, sine isn't one of the ones that we would necessarily use this for, but this specific one you might. So I'm going to stop here with this. But again, remember what we're doing. We're going to find those entries, then we're going to multiply them by original function, which was sine, and then integrate to find what we multiplied to the fundamental set. But let's kind of go back real quick and talk about why this still might be the method you want, even though undetermined coefficients could work. Let me go back to the original differential equation. We had the fourth derivative. We were adding to it the second derivative, sorry, 2 times the second derivative, plus the original function is equal to sine. I want you to think about what form your guess would have to take. So since it's sine, in general, we would want a sine plus b cosine. But remember that sine and cosine, those things actually came in the fundamental set. So I'm going to have to multiply by t's, but t isn't enough because t sine and t cosine were in there. So I'd actually have to multiply this by t squared. So this could start getting ugly when we start getting the repeated roots. This one's not going to be terrible, but it's still not going to be that pleasant if you want to go through this all the way and solve for a and b. The undetermined coefficients will get you the same thing as the variation of parameters will. So I'll leave these for you to kind of verify that you get the same thing either way. Okay, so moral of the story. Variation of parameters still works. It still works because of the same reason. We're still doing the same thing. We're still finding an inverse of the Wronskian. We're multiplying that to a matrix that contains a bunch of zeros and then the function that we're equal to. And then the results of that get integrated to find our u's. So we're doing exactly the same thing. It's just more, lots more. Because now these matrices are much bigger. They're a little bit more complicated. They take a longer time in terms of finding their inverses, but remember, you really only need the last column. So when you're doing this, you'll see that there's a homework set for these. I think there may be 4 questions on there. Might only be 3, I'm not sure, but not that many. When it comes time to doing those, please feel free to use your technology, okay, to find that A inverse. Because this isn't what I'm testing you on. I'm not caring to see if you know how to find the inverse. I know you could if you needed to, right? But realize that if you're ever in a situation where you don't have the technology, just jump to that last column. And it can be fast, especially depending upon what the entries are. Like if you ever start getting zeros in your matrix, in your Wronskian matrix, you should be happy. Right, so that's going to happen when you have polynomial fundamental terms. So like when you go through the process and you get things like t in your fundamental set, you're going to be super happy. Because if t's in that fundamental set, then so is 1. And both of those things are going to go away real quick like. They're going to turn into zeros, which is going to make finding the determinant way easier and then finding the inverse way easier and so on. So polynomials are your friend, no doubt. The trig functions themselves are not terrible because a lot of times, like in this example, they reduce down using identities. Like think about that one. We found its determinant was 4. That's it. Every entry had sines and cosines and t sines and t cosines and I mean, bleh, right? But when we actually found its determinant, it was 4. Super easy. So with the trig functions, watch for that. Watch for what you can reduce out using identities because that can be kind of useful. Anyway, so at the end of the day, same stuff, just more, which is pretty much what we've seen with everything with these higher orders. Same stuff, just more. Okay, well, I think I'm going to stop here. We're losing steam. So here's where we are next week. We got 1 week left. Next week, I'm going to show you systems of differential equations. And we'll look at how we find those solutions. We're going to bring back a good friend of yours from linear algebra. You may remember eigenvalues and eigenvectors. At least you hopefully remember those terms. Well, I'm going to show you a use of them. We're going to need eigenvalues and eigenvectors in order to solve systems of differential equations. So that's what we're going to do next week. But then, you know what? After next week, there's a final exam, only for those of you who need to take the final exam, right? Remember the deal with the homeworks. So we're almost there. We're almost there. All right, so I'm going to go ahead and stop our recording for